Hello everybody, my name is João Rego and I am here to present the article entitled Development of a Modular Multilevel Cascade Converter based on Full-Bridge Submodules with a common DC bus. The work was done by me, by my colleague Fabio Pereira, by Professor Luís Barros, by Professor Dr. António Pina Martins, and by Professor Dr. Gabriel Pinto. The structure of this presentation is very similar to that of the article. Therefore, this presentation is organized as follows. Initially, an introduction to the research topic is made and the advantages of the multi-level modular concept are shown. In the next, the MMCC topology used in this study is presented and the control algorithms implemented are described. The next topic presents the simulation results as well as the methodology for the MMCC analysis based on cascade transformer. After that is shown the experimental results of the MMCC. And finally, the main conclusions of the study are presented as well as some suggestions for future work. The growing technological evolution combined with the increase in the demand for electrical energy encouraged the investigation of more efficiency and effective power electronics solutions. 2- and 3-level DC-AC power converters are the most widely used topologies. However, in these converters, the content of the output harmonics is dispersed, which causes less loss in the system. For this reason, conventional converters are not viable for high power and high voltage applications. The multi-level converters present themselves as innovative solutions to mitigate dimensional problems. In the literature, there are several topologies of this converter, some of which are shown in the figures presented. As already mentioned, this study focused on the MMCC with common DC bus and cascade transformers. The modular and multi-level concept allows the connection of different submodules with the number of added submodules being adjusted to the desired voltage, and the more submodules added, the more voltage levels the MMCC can synthesize. It is possible to obtain a waveform closer to the sinusoidal one, which minimizes the harmonic spectrum, being more concentrated on the fundamental component and the switching frequency. Therefore, it is possible to reduce the dV/dt variations in the output, allowing the integration of smaller passive filters and more robust semiconductors. For these reasons, system losses are lower and efficiency is higher, which is important for high power applications. As already mentioned, the topology of MMCC used was the full bridge with cascade transformers and a common DC bus. This topology is presented in the figure. This converter consists of the parallel association of 3 full-bridge submodules sharing the same DC bus. The output of each submodule connects to the primary side of a power transformer, while the secondary side is connected in series with adjacent transformers. In this study, these power transformers have a transformation ratio of 1:1 and are used to create the multi-level feature since there is only one DC bus. Due to the versatility of changing transformer transformation ratios, it is possible to obtain different output voltage levels even with few submodules. Sharing a single DC bus between different submodules facilitates control algorithms as well as the integration of other power converters. From an implementation point of view, the use of just one DC bus and the existence of a common reference for fully controlled power semiconductors makes implementation easier. Furthermore, this topology makes it possible to synthesize a sinusoidal output current at lower switching frequencies. However, due to the use of a power transformer for each submodule added, the system implementation costs can be higher. Another disadvantage of using transformers in this topology is that they are not suitable for variable frequency applications. MMCC control algorithms that interface with the power grid need to be synchronized with the critical component for accuracy and efficiency operation. The synchronization algorithm must detect the signal phase as quickly as possible, and the synchronization process must be continually updated to increase efficiency. The synchronization technique used in this study was the enhanced phase locked loop, or EPLL. This technique can detect the phase and amplitude of the fundamental component of a given input signal. The output signal is sinusoidal and in phase with the fundamental component of the input signal, even if contains harmonics. The main purpose of the MMCC is to inject energy into the power grid. Therefore, the MMCC will have the function of synthesizing a sinusoidal current in phase opposition with the voltage power grid. The reference current is obtained through this equation. After calculating the reference current, it is necessary to control the output current in the converter. Therefore, a PI current control algorithm and the PWM phase shift carries modulation technique were used. In this section, the simulation results of the implemented topology are presented and analyzed. To obtain realistic results, it is important to get an accurate model of the transformer, which is a key component in the studied topology. It was necessary to measure with the windings in series, which is terminal B connected to terminal C, and measure from A to D, and in anti-series, which is terminal B connected to terminal D, and measure from A to C. When measured with the winding in series, a value of 4.9 Harris was obtained. On the other hand, when measured with the winding in anti-series, a value of 3.6 mH was obtained. After obtaining the value of the inductance with the windings in series and in anti-series, it is possible to calculate the self-inductance of the windings and the mutual inductance between the windings. The self-inductance value of the primary winding, as well as that for the secondary winding, the mutual inductance is 1.22 Harris. With these calculated values, it is now possible to calculate the value of the coupling coefficient in order to finally obtain the values of the leakage inductance and the magnetization inductance, presented in the equivalent model of the transformer. The coupling coefficient between the windings has a value of 0.99, the leakage inductance of the primary winding as well as that for the secondary winding has a value of 1.8 mH, and the magnetization inductance has a value of 1.22 Harris. The windings resistance of the equivalent model of the transformer were measured by a precision multimeter. The value of the primary winding resistance is 3.1 ohm, and the value of the secondary winding resistance is 3.8 ohm. This table presents the values of the main components and used in the computational simulation of the study topology. The value of the components used were obtained to be the closest to those used in the laboratory prototype. The implementation and respective simulation of the PLL algorithm for synchronizing the voltage of the power grid were carried out, and the simulation results obtained are presented. As can be seen, the PLL algorithm quickly synchronizes with the frequency and phase of the fundamental component of the voltage power grid and determines the amplitude in a maximum of 4 cycles. Using real or ideal transformers in simulation can make a difference. In this slide is shown the MMCC output voltage using an ideal transformer. As can be seen, the use of 3 submodules in series allows, as predicted, the existence of 7 voltage levels at the output. It should be noted that with the ideal simulation model, it is possible to obtain an MMCC output voltage with a maximum value of 180 volts, 3 times the DC bus voltage. For a real transformers model is shown the MMCC output voltage. In a real application, transformer windings contain inductance and resistance which cause losses. The influence of these parameters can make it difficult to visualize the output voltage levels because of the slower dVdt response. Even so, the presence of inductance in the transforming windings allows to obtain a voltage waveform close to a sinusoidal. After completing the system initialization process, the MMCC control is fully functional within 0.5 seconds, as is highlighted in this slide. The MMCC will have the ability to inject energy into the power grid depending on the reference power. Therefore, with the introduction of a power value, the active power injected into the power grid must follow the reference, as shown in this figure. Now it is possible to see that the synthesized current follows the reference current. It can be concluded the correct operation of the current control algorithm implemented, resulting in a grid current with a low harmonic distortion. Moreover, it is highlighted that the PE current control algorithm allows the MMCC to synthesize a sinusoidal current 180 degrees lag in relation to the voltage power grid. Once the computer simulations have been validated, all the hardware was assembled, highlighting the control system and the power system. In this section, I presented some experimental results of the MMCC. This slide shows a general overview of the laboratory workbench, where the hardware was assembled and tested for this article. This table shows the specifications of the operation conditions of the laboratory prototype implemented for the experimental tests. The microcontroller used was the control card F28379D from Texas Instruments. As already mentioned, it was used the phase shift carriers PWM technique, and for the microcontroller, 6 carry waveforms were implemented with a frequency equal to 1 kHz and out of phase with each other by 60 degrees. To produce a sinusoidal current in phase opposition relativity to the power grid voltage, it is necessary to produce a signal synchronized with the fundamental component of the power grid voltage as already mentioned. Thus, the synchronism of the PLL signal algorithm with the voltage power grid is shown in this figure, based on the algorithm used in the computational simulations. Note that the variables were visualized using a DAC with a 0.016 volt per volt scale. In an ideal scenario, the MMCC output voltage will be 3 times the voltage of the DC bus, which is 180 volts. However, considering the voltage drops in the IGBT devices and in the low frequency transformers, the output voltage presents a similar waveform to the obtained on the real model simulations. Analyzing this figure, it can be concluded that the MMCC can synthesize all the expected voltage levels with a maximum voltage variation up to 106 volts and a minimum of minus 118 volts. To inject energy into the power grid, the current synthesized by the MMCC must be in phase opposition relativity to the voltage power grid. Moreover, the MMCC output voltage must be higher than the peak value of the power grid voltage. The experimental results obtained for the injection of energy into the power grid with the variation of power reference from 80 watts to 110 watts are shown in this slide. A power reference of 80 watts and 100 watts was given to the MMCC. Considering the power grid voltage, the control system determined a reference current of 1.85 amperes of peak and 2.3 amperes of peak respectively. The results are presented in this figure. This proves the correct functioning of the MMCC, where the grid current follows the reference current. Note that these variables were visualized using a DAC with a 1 volt per ampere scale. So, this presentation demonstrated the development of a modular multi-level cascade converter composed of full-bridge submodules with a common DC bus and with a low-frequency cascade transformers. The MMCC was first validated based on computer simulations, with the entire methodology being presented as well as the control algorithms. Regarding the simulation model, the real parameters were used, namely in the transformers equivalent model. As such, it was necessary to carry out experimental tests and measurements in order to obtain the important parameters for the implemented model. The simulation model was validated based on experimental results, obtaining experimental results similar to those of the simulation. However, as the main technical conclusions of the work, it can be concluded that the low-frequency transformers generate audible noise due to the vibrations during the operation of the MMCC and have low efficiency. So, for future work, in order to maximize the system efficiency, the inclusion of LCL filters at the input of each transformer in order to apply a sinusoidal waveform to its low-frequency transformer will be studied. This solution could increase transformer efficiency despite increasing losses in passive filters, since they would have to be replicated depending on the number of submodules added. This solution, instead of adding square waves, presenting a stereo output waveform, would add sine waves, which could reduce the output harmonic spectrum. However, this solution eliminates one of the premises of the MMCC, which is the frequency multiplication applied to the output filter, reducing its weight, volume and cost. Another solution will be the study, design and development of a medium frequency transformer for the specific application. For example, the use of amorphous ferromagnetic materials will present an added value since they allow a higher magnetic flux density, allowing operation with higher switching frequencies. And finally, thank you for your attention.